Okay, so welcome to the continuation of the cardiovascular physiology lecture, and now we're going to be talking about the cardiac action potential phases. So the first phase we're going to talk about is phase 0 right here, which goes from the -90 to that +30 like we were looking at on that graph before. Here we have a rapid change from -90 to +30 millivolts. This results from a change in membrane permeability to sodium, which allows more sodium into the cell from the outside of the cell. The sodium that's coming into the cell leaves the negative chloride ions behind on the outside of the cell, thus the cell becoming less negative and then becoming more positive in comparison to the outside of the cell membrane. Okay, so again, we are rushing sodium into the cell here to make the inside of the cell less negative, and then we become positive. All right, now let's move on to phase 1, which is this section right here. Okay, this excess positive charge inside the cell and the negative charge outside the cell promotes the outflow of potassium. Okay, so we're going to promote the outflow of potassium. Enough potassium moves out of the cell to balance the +30 millivolts and creates a charge of 0. So we're almost at a charge of 0 here. So we have shot up to +30, then more potassium moves out of the cell, and then we're at about a 0 millivolt section right here. This leads directly to phase 2, which is the only time during the transmembrane action potential that a charge of 0 occurs. It's right here. Okay, during phase 2. So now let's talk about phase 2. Phase 2. The permeability of sodium and potassium to the cell are about the same here. It's an equal exchange, both moving in and out of the cell at this point. So this lasts until permeability returns to normal resting state. Okay, so then now let's move to phase 3, which is over here. Potassium moves out of the cell because the permeability is back to what it was at the beginning, right? So remember we talked about 100 potassiums leaving the cell with 1 sodium coming into the cell. So now phase 3, what's occurring is potassium moves out of the cell because the permeability is back to what it was at the beginning. So there's no more charge holding the potassium in. The potassium flow follows its concentration gradient easily, right? So 100 potassiums out of the cell for 1 sodium in, like we talked about before. So this helps move this potential back to negative again, right? Because now we're flowing something positive outside of the cell because we're at we're going back to resting membrane potential, which we have a large amount of potassium leaving the cell. So we're becoming more negative again. So there's still some extra sodium inside the cell, so thus the ionic state is not exactly what it was here. This is resting membrane potential, right? So through phase here, even though we're becoming more negative, there's still some sodium that is being left in the cell. That's why it's not here yet until we get rid of the rest of that sodium. Right, so let's go to phase 4. This is a correction of the ionic state. We are now back to resting membrane potential. The expulsion of sodium from inside the cell has occurred. The movement of some potassium back to create correct ionic balance. And then the movement of, there's a problem with the movement of ions due to the decreased permeability. So movement occurs against the chemical gradient, which is the active transport, which requires the expenditure of energy, right? So now everything is kind of going back to normal, 100 potassiums out for 1 sodium in, and then our sodium-potassium exchange pump is also working. Okay, so late phase 4 is a complete time of recovery. Okay, so you will see I also uploaded this for you up onto Blackboard, which gives you the diagram and what we had just talked about for each of the phases. But it's important for you to follow along with me so you can understand each one of the phases relative to what we're talking about, what's going on within the cell itself. Okay. All right, now we're back. All right, so let's make 3 summary statements about electrical activity in general. So 1, Resting state in cardiac cells is classified as the polarized state, and anytime anything is polarized, the inside of the cell is negative relative to the outside of the cell. 2. The inside negativity is lost during depolarization, and it is the most basic fundamental electrical activity occurring in the myocardium of the heart. Depolarization causes the action potential, which is a moving wave of electrical current from one cell to another. 3. Resting polarity is attained during the repolarization phase. And again, we have two segments, the absolute refractory period and the relative refractory period. Okay, so those are three big summary statements that we pretty much just went over with all of that intro to electrophysiology material. So now we're going to move on to talk about different types of cardiac cells. So any segment, waveform, or interval we see on an ECG is the result of depolarization and repolarization of different tissues. So 1, let's talk about pacemaker cells. These cells initiate one cardiac cycle. Okay. 2, electrically conducting cells are cells through which the electrical current will pass. The current will move at a great speed due to the presence of gap junctions that line up between the cells. Remember, let's reverse back to neuromuscular physiology when we talked about how there were some cells that have gap junctions. This is a place where cells have gap junctions. Unlike at the skeletal muscle tissue level, they have that space where that amorphous substance is, where the acetylcholine has to go and grab onto the alpha receptors on the opposite side of the cell membrane. This is different. We have gap junctions within these electrically conducting cells within the heart because we need this electrical signal to progress in an extremely fast manner. So that's why these help move that electrical current very, very quickly. Now 3, true myocardial cells. These are the cells that actually respond to the moving weight of electrical current. These cells generate tension, they generate force, and these are the cells that allow us to say contraction coupling has taken place. All right, so now we're going to talk about the electrocardiogram and its characteristics. So all ECG configurations show 3 characteristics. 1, duration, 2, amplitude, and 3, configuration. So what this whole thing looks like. Duration this represents timing. This is measured on the x-axis, measured in milliseconds. Okay, so down here, x-axis is the time. So this is a time frame measured in milliseconds. Amplitude is represented on the y-axis up here. Okay, and this is measured in millivolts. Okay, so how many millivolts is occurring at one portion of the tissue at what time? And configuration, is this what gives them shape? So this is what gives this whole thing their shape. All right, so let's go what the ECG tells us. So here, let's start with the P wave. So the P wave is right here. So the P wave, this represents the atria depolarizing. Okay, the first half of the P wave, so the upstroke of the P wave, is, all right, sorry, I had to get myself straight right there for a second. The upstroke of the P wave is the right side of the atrium depolarizing, and then the downstroke of the P wave is the left side of the atrium depolarizing. So this flat portion between P and Q represents electrical neutrality. So this means nothing is depolarizing and the flow of electrical current slows down. Okay, so we have a point of electrical neutrality here. Then we move on to the QRS complex, which is right here. The Q wave, the R wave, and then the S wave all makes that QRS complex. Okay, this is the entire ventricles depolarizing. The Q wave is the septum depolarizing. And then we have the left and the right ventricles depolarizing. Okay, so then we enter another segment of electrical neutrality. And then the T wave represents the ventricles repolarizing. So all of the ions, like we just talked about, the absolute and relative refractory period are in here. Absolute refractory period actually starts right here, right over here. But then the relative refractory period is at the end of the T wave. Okay, so however, the T wave represents the ventricles repolarizing. So those ventricle tissues in the cardiac cells are where the ions are all going back into place. Okay, so you may ask, well, where is the repolarization of the atria? So the atria depolarized here, and then we have some neutrality, and then we have the ventricles depolarizing here, and then we have ejection and all that other stuff, and then we have some neutrality. And then the ventricles, this is representing the ventricles repolarizing. Well, where is the atria repolarizing? Where's their wave segment? It's actually hidden within the QRS complex, okay? Since this is a smaller amount of tissue mass that has to depolarize anyway, it is, while that is repolarizing, it is not represented up on the ECG. Okay, because what takes over are a large muscular mass in the heart, which is the ventricles. It is going to show the ventricles depolarizing, nothing to do with the atria repolarizing. So you may ask where that is, but it is hidden within that QRS complex. That's where the atria is repolarizing. And then we go over here, and then we have the ventricles repolarizing. Okay, so continuing on what the ECG tells us. So let's look here, let's look closely at after we just went over what each of these waves and segments mean, let's go over what each one of these little boxes and stuff means. So the distance between borders of the little squares are 0.04 seconds, okay? Between two heavier black lines that you will see on some ECGs, which is not represented right here, but you will see heavy black lines every so often on ECG paper. That represents 0.2 seconds. So 5 little squares put together. So it puts in 1, 2, 3, 4, 5. You would see a heavy black line. 1, 2, 3, 4, 5, and heavy black line. That represents 0.2 seconds. And each one of these boxes represents 0.04 seconds. Okay. Each little square on the y-axis going up represents 0.1 millivolts. Okay, so 0.1 millivolts. So 10 of these added together would give you 1 full millivolt. Okay, the height of the amplitude right here, so of these waves, the height of the amplitude represents how much tissue is depolarizing and repolarizing. So the first wave, when we already talked about the atria depolarizing, the P wave is not that high in comparison to this QRX complex. Look, this wave compared to up here. Okay, the first wave is not that high because this is the atria, and that means that there's a lot less tissue to depolarize than there are in the ventricles. So there's a lot more ventricular tissue to depolarize compared to the atria. Okay, and then the repolarizing of the ventricles has a decent wave because repolarizing is still enough to put onto the ECG form where everything's going back into place. So there's enough ionic movement that is going to be represented on the ECG. So now you can see that the atria had a smaller depolarizing wave. So then that's why it's hidden in this complex right here. Right, so we went over those waves and the segments, right? So a segment is where electrical neutrality is occurring, right? And then we have this PR segment, and then this ST segment, right? So it's between the depolarizing of the ventricles and the repolarizing of the ventricles. And then we have electrical neutrality between the depolarizing of the atria and the depolarizing of the ventricles here. Now, when we talk about an interval includes some sort of depolarizing or repolarizing of tissue and a segment of electrical neutrality. So the PR interval here includes the atria depolarizing and then some electrical neutrality right before we go to the ventricular depolarizing. Now, the QT interval has the ventricles depolarizing, and we have then some electrical neutrality and then the ventricles repolarizing. Okay, so just think of it. The segment represents electrical neutrality where nothing's really going on. We have an equal distribution of ionic balance, but then an interval includes some sort of depolarization or repolarization of a tissue plus some sort of electrical neutrality. So a segment is just that neutrality alone, where an interval also includes some sort of depolarizing or repolarizing of tissue. Okay, next we're going to get into the different components of the cardiac tissue and the cells. So we're going to talk about the SA node, AV node, and the bundle of His, and how the electrical current flows through the heart. So we will do that on the next video.